Okay, we're going to go ahead and get started here on 6.2, the homework. Going to be evaluating some trig integrals. First one, number 1, is integral sine squared x times cosine cubed x. So sine squared x times cosine cubed x. See if I can find any good markers here. Dx. All right, so going through the steps, the procedures that the notes give you says that if you have sine or cosine raised to an odd power, right? Or sorry, the first step says if cosine is odd, then we're going to factor out one of the cosines. So we do have cosine as an odd power here. So we'll go ahead and factor out a cosine here. So let me take one cosine. So this integral is equal to sine squared x times cosine, times cosine squared x times cosine x dx. So I've factored out one of the factors of cosine, and I'm going to make a substitution that u will be equal to sine x. The derivative of that is cosine x dx, which I actually have right here. So now it's just a matter of rewriting everything here in terms of sine so that we can replace these things with u's. So this is already going to be u squared. Cosine squared, though, needs to be switched. So what I'm going to use is the Pythagorean identity, rewriting cosine squared x as 1 minus sine squared x, and then rewriting everything else. And now you can see this is going to be u squared, then 1 minus u squared, and then this here will be the derivative of u, so du. So now I'll go ahead and rewrite this integral. So this will be equal to, in terms of u, it'll be equal to u squared times 1 minus u squared times du. And now this is just powers. This is just a polynomial in u. So what I can do is I can distribute the u squared through to remove the parentheses. So u squared minus u to the 4th du. And then I just integrate those term by term, and I use the power rule. So the antiderivative now is 1/3 u cubed minus 1/5 u to the 5th plus some constant. And now just replace u with sine x. So we get 1/3 sine x, but cubed, so we put the 3 here, then minus 1/5 sine x, but to the 5th power, so put 5 here, and then plus my constant of integration. So that's number 1. Now I'm going to do number 2. So for number 2, we have, let's see here, sine to the 3rd, cosine to the 4th. Was it theta? They're using theta. Sine to the 3rd theta times cosine to the 4th theta d theta. So this time, the sine is the thing that's being raised to the odd power because it's being cubed. So this time I will factor out a single factor of sine instead. So this can become sine squared theta, cosine to the 4th theta. Factored one sine out, so here it is, sine theta d theta. And then I will make the substitution that u will be cosine theta this time. And the derivative of that is negative sine theta d theta, which we almost have. We have a positive, and this is negative, right? So I'm going to just multiply both sides by -1. I need a new marker. I don't have any good markers around here. And so I can replace the sine theta d theta with negative du. I can replace the cosine theta with u, so that'll become u to the fourth. I just need to be able to get rid of that sine squared. So again, I'll use the Pythagorean identity to turn sine squared into 1 minus cosine squared. And then I still have the cosine to the fourth. Then I still have sine theta d theta. And then at this point, we can rewrite the entire integral in terms of u. So this integral becomes, in terms of u, 1 minus u squared times u to the fourth. Then this is negative du, so I'll put a negative on the outside of the integral, negative du. And then what I'll do is I'll multiply u to the fourth through. So this becomes negative integral u to the fourth minus u to the sixth du. And then one more thing I'm going to do before I integrate, because this is a negative, is I'm going to multiply it back through, make that a minus u to the fourth and a plus u to the sixth. And then I'm going to rearrange the order of things. So that integral becomes positive u to the sixth minus u to the fourth du. And then at this point, I integrate using power rule. So this will be equal to 1/7 u to the seventh minus 1/5 u to the fifth plus c. And then this is going to be 1/7. U was cosine theta, so cosine theta to the seventh minus 1/5 cosine theta to the fifth plus c. I think that was an exam problem, if I'm not mistaken, for my face-to-face class. And that's it. We're done. All right, so moving along. Number 3. All right, for number 3, let's see here if I can maybe get a decent marker here. I doubt it. Okay, integral sine to the seventh theta, cosine to the fifth. And they had limits of integration numbers there, but we're ignoring those for now. So what I'm going to do now is realize that I have both the cosine and the sine that are both odd powers. And so really it's up to me to decide which one I want to use. Do I want to use the sine or the cosine as my u? And I have the choice because they're both odd. So I'm going to go ahead and use the sine because I like the derivative of sine. The derivative of sine is just cosine. I won't have to worry about any negatives. So I'm going to let u be equal to sine theta. Du is equal to cosine theta d theta. So in doing this, I need to peel off that cosine, one of the cosines here, out, so that I can have my du sitting there. So cosine theta d theta. And now it's just a matter of turning everything in terms of sine. So sine to the seventh is no problem. Cosine to the fourth, though, I can't use that. So what I'm going to do is I'm going to realize first that cosine to the fourth is really cosine squared, and then cosine theta d theta. Now I can use Pythagorean identity here. So we have integral sine to the seventh theta, and then this is 1 minus sine squared theta, but then that entire quantity squared, and then cosine theta d theta. And now I have everything in terms of u. In terms of sine, which is u. So this will be u to the seventh, this will be u squared. And then this right here is exactly du. So I'm going to rewrite the integral now. I'm going to rewrite it in terms of u. So this becomes u to the seventh, that's this, parentheses, 1 minus u squared, parentheses, squared. and then cosine theta d theta is du. And this is very much like the last problem, but I can't distribute the u to the 7 through because I have a squared here. So I actually have to square that first. And because I can square it, that's what makes this problem doable. If that were to the 100th power, I'd have to do something else. So when you square this, right, you have to multiply it times itself. You get 1 minus 2u squared plus u to the 4th du. And then you can distribute the u to the 7th through. So you get integral u to the 7th, it's here, then minus 2 u to the 9th, I'm adding the exponents, plus u to the 11th du. And then I can integrate using the power rule. So I'm ready to actually take the antiderivative now. So this will be 1/8 u to the 8th. This one, I'll ignore the -2. That's going to become 1/10 u to the 10th, but I have a -2 out front. So -2 times 1/10 u to the 10th. And then this one's just plus 1/12 u to the 12th plus some constant. And this right here, when we put these together here, this will be a minus 1/5 because we're multiplying. So now I'll just replace all my u's with sine. So I should get 1/8 sine theta to the 8th power. And then here we said this is going to become minus 1/5 sine to the, 10th power theta. And then plus 1/12 sine to the 12th theta plus a constant of integration. Okay, that was 3. Let me take a look at 4. I can already tell that marker's not going to be good. Try a blue one. Integral sine to the 5th. Oh, wow, no. Okay, I don't know why people don't throw these things away. Oops. Sine to the 5th x dx. All right, so I have sine to an odd power, so I will factor one factor of sine out, right? But we have a problem here because we're supposed to let u be equal to cosine x, and I don't have, because what? The derivative of this is negative sine x dx, which I almost had there. I'm off by sine, so negative du will be sine x dx. But I don't have a cosine here. But that's okay because I can rewrite that sine in terms of cosine. I'm going to use the Pythagorean identity to do it. This is getting annoying. Hang tight, I'll be right back. All right, so what I'm going to do here, I'm going to throw all these markers away because none of them are good. So you're going to rewrite the sine to the 4th there. Maybe you've done this on your own already. You've been waiting for me. Rewrite it as sine squared squared. And then the sine squared you'll turn into 1 minus cosine squared. All right. So this sine to the fourth is sine squared x squared. Then I have sine x dx. So these markers are good, but they don't last very long. All right, and now this is integral 1 minus cosine squared x squared times sine x dx. So sine to the fourth is sine squared squared. Sine squared is 1 minus cosine squared, and then squared. So now I should be in business. I make my substitution that u is cosine x. So the integral becomes, in terms of u, integral here, 1 minus u squared squared, and then this right here, remember we have the negative, don't forget that negative, negative du. And now I will expand this out, multiply it out. So I have equals negative integral. We get 1 minus 2u squared plus u to the fourth du. And that negative on the outside, I could leave it there. I like to bring it in if I've got a polynomial like that. I just go in there and change all the signs of everything. So this is equal to negative 1 plus 2u squared minus u to the fourth du. And now I'll do my integration. Remember, u was sine x, I just erased it. And so we get antiderivative of negative 1 is negative u. Antiderivative here, we get a 1/3 u cubed, but there was a 2 out there, so 2/3 u cubed. And here I get minus 1/5 u to the fifth plus a constant. And u in this problem was sine. So I will say this is negative sine x plus 2/3 sine x to the third, and then minus 1/5 sine x to the fifth plus a constant. And that is it. These write good, but they don't erase very good. Put a little elbow grease into this to get this off. My goodness. Okay, number 5. Number 5. Cosine squared. This was a test problem. Yeah, it was. All right, so on this one, we don't have an odd power. Okay, so when we don't have an odd power for sine or cosine, we have to use a different technique. And the different technique is to use the power reducing formula. So that means I'm going to use this formula. Cosine squared theta equals 1/2 times 1 plus cosine 2 theta. And we talked about that in class. So this formula allows you to take a squared on a cosine and get rid of the squared. So you notice this is not squared. But in the formula, you're going to get a 2 theta inside the argument. And then there's a bunch of other crap out here too. But it allows you to reduce the power, and that helps us because when we integrate, we can integrate that, relatively easily, I should say. All right, with relative ease. That's what I really should have said. Okay, so replacing this expression with this, the 1/2 is going to come out of the integral. I will have in here 1 plus cosine 2 theta, and that's it, d theta. And this integral, super clean. I can do the antiderivative of each one because I have addition, so it's 1/2, here's my antiderivative, and then let me go ahead and figure out what these are. Antiderivative of 1 with respect to theta is just theta. The antiderivative of cosine we know is sine, but because that's a linear expression inside, I have to scale by 1/a. And then this plus c, and distribute the 1/2 through, and you get 1/2 theta plus 1/4 sine 2 theta plus c. We're done. Number 6, sine squared of 1/3 theta. Sine squared, how do they write that? 1/3 in front? Yeah, 1/3 theta d theta. This problem is going to work exactly like the last one, except, well, because it's squared, we have an even power, not an odd, except that we have to use a different formula. We have a different formula for reducing the power on sine. It's this, sine squared theta equals 1/2, that's the same, 1, that's the same, minus, that's different, cosine 2 theta. So everything else in the formula is exactly the same as the last one, except it's minus. And it is a cosine here, it's not sine. So this is the formula. Notice I have 1/3 theta though. Okay, so that's going to be a little bit different over there. So this becomes integral, I have a 1/2 that comes out, 1 minus, and then cosine of 2 times whatever angle was here. So just 2 times that, which is 2/3 theta, d theta. So I just double the angle, right? 2 times 1/3, that's 2/3. And now, again, I can integrate this with relative ease. 1/2 here. Antiderivative of 1 is theta. The antiderivative of cosine is sine, and I have a minus here. And also, I have to scale, because this is linear in here, I have to scale by 1/a. So I do 1/2/3, which comes out to be 3/2. And then plus c. And then I can distribute my 1/2 through. And when I do that, I get 1/2 theta, distribute here to here, minus 3/4 sine 2/3 theta plus a constant. That's it. We're done. All right, number 7, cosine to the 4th of 2t dt. Ugh. I already know this is going to be ugly. Cosine to the 4th of 2t dt. All right, now the reason it's going to be ugly is because it's cosine to the 4th, so I can't do what I did when it was odd and just pull out a cosine. Because it's even, I know I'm going to have to use that power-reducing formula. The power-reducing formula for cosine I had up on the board just a second ago is this one. I'm just going to put 2 theta without parentheses. So since I have a 4th power, I'm actually going to wind up getting that thing, this thing, squared, which is going to give me another cosine squared at some point, which means I'm going to have to do the power-reducing formula again. So I already know, because this is to the 4th power, I'm going to wind up using that formula twice. So let me show you. So first of all, I'm going to rewrite this as cosine squared 2t, but then that's being squared. I could use parentheses, but I use brackets just for fun. Okay, so this thing squared, and then squared is to the 4th power. Now, we already know inside that bracket that we get a 1/2, 1 minus, plus cosine of 2t, okay? That's what this is with the formula. Oh, sorry, hold on. Forgot to double the angle. I have to double whatever angle was in here, so that's not 2t, that's actually 4t. I'm glad I caught that. And then that's what's in my brackets, and that's being squared, and then dt. Okay, so this becomes this, but it's still squared. And now what I need to do, I cannot integrate. I can't pull the 1/2 out even because it's being squared. So I can't integrate each of these one by one because of the squared also. So let's try and take care of that squared. First of all, because this is multiplication, I can square this and square this. So that means it becomes integral 1/2 squared is 1/2 times 1/2, that's 1/4, times this thing squared is 1 plus cosine 4t, all of that squared. Notice the squared is no longer on this. We already took care of that. And then dt. Now, the 1/4 now can come out. So I have 1/4 that comes out of this problem. So 1/4 integral. Now what's still here? 1 plus cosine 4t, that quantity squared. Now I have to actually square this, which means I have to multiply it times itself. So let me take a little break here and do that. That means I have to do 1 plus cosine 4t times 1 plus cosine 4t. And then I FOIL 1 times 1. 1 times cosine 4t is cosine 4t. 1 times cosine 4t again is cosine 4t. And then the last one, which is very important, cosine 4t times cosine 4t is cosine squared 4t. It is not cosine squared 16t squared or anything like that. You're multiplying something times itself, which means it's that quantity squared. I can combine the middle two terms together to get 1 plus 2 cosine 4t, then plus the cosine squared 4t. All right, so this integrand becomes this integrand, and now I've split it up. I have 1, 2, 3 terms. So what am I going to be able to do with that? Let's see. Goodness. Okay. Integral. 1/4 was out here. All right, now all this. 1 plus 2 cosine 4t plus cosine squared 4t dt. So now we look at each one. Can we handle each one? Antiderivative of 1 with respect to t is just t. The antiderivative of this I should be able to do because it's just a cosine function. I've got an a in here, so I'm going to have to scale when I do this. But this one is a cosine squared, and I can't integrate that. And that's the one I'm going to have to do the formula on again. So let me take care of these two first. I'm actually going to find the antiderivative here. The antiderivative of 1 we said was t, but then times 1/4, because that 1/4 goes to all of these, right? So I have 1/4 t, no more integral sign there, right? Then the antiderivative of this one, let me just jot it down. I have a 2. The antiderivative cosine is sine of 4t here, but then I have to scale by 1 over a, right? So that's going to become, these two together is 1/2 sine 4t, but then I have the 1/4 that distributes through and hits this and becomes a 1/8. So this next term is going to be 1/8 sine of 4t. So I've taken the antiderivative of the first two terms and I distribute a 1/4 through. This one I cannot find the antiderivative of right away. So I'm going to keep the integral sign on this one, remembering I had a 1/4 out here. So plus, right, plus 1/4 cosine squared 4t dt. I wonder if this works any better. Oh no, that does not. All right. Okay, at this point, I'm going to need to bring that formula back in. Okay, the formula is going to allow me to reduce the power on this one right here. So, using the formula, this integral becomes a 1/2, then in parentheses 1 plus cosine, and then double the angle. doubling that angle, I now have 8t dt. And the good thing here is I can pull the 1/2 out. It'll join up with this 1/4. And then I can integrate those term by term. So let's do that on the next line. I'll pull the 1/2 out, so I'll rewrite everything. Actually, I'm gonna save myself some time. I pull the 1/2 out. This becomes a 1/8. And then this integrand right here is what's in parentheses here. So 1 plus cosine 8t dt. All right, now I have the pleasure of integrating each of these and just remembering that I have a 1/8 out here. So I'm getting to an answer here eventually. Just rewrite all this first. Plus 1/8. Now here's my antiderivative. Antiderivative of 1 with respect to t is just t. And then antiderivative of cosine of 8t is sine of 8t. But I have to scale it out in the front, 1/8. And then I've done the antiderivative, so plus c. And now what I'll do is I'll distribute that 1/8 through. You can see why I went, ugh, when I saw this problem. I kind of knew where we were headed. 1/8 t here to here, and then here to here is 1/64 sine 8t plus c. There is one more thing we can do. We can take 1/4 t and combine it with 1/8 t. You can't put the signs together because they have different arguments, 8t and 4t, so you can't put those together. But 1/4 t plus 1/8 t is what? 3/8 t? So let me just get rid of this one. And I'll change that to a 3/8 out here. 3/8 t. So it's this plus that plus c. All right. I've got to go in like half an hour. Got a meeting. Let's see what else I can do here. Look at number 8. This homework assignment is going to take forever to get through. If I do all the odds and evens, this is going to take a long time. Okay, number 8. Integral 2 minus sine theta, that whole quantity squared d theta. All right, so you look at this and you're like, okay, I could take the antiderivative of these individually, but it's being squared, so I can't do that. So why don't we just square it out? And I'm going to try and save us some time. I'm going to square this out in my head, and hopefully I'll get it right. 4 minus 4 sine theta plus sine squared theta d theta. So if you take this times itself, set them up, do the FOIL, collect like terms, you should get that. And now you look at each of these. Yes, I can find the antiderivative of 4 with respect to theta. Yes, I know the antiderivative of sine. Sine squared, on the other hand, I don't, because it's squared, so I have to use that power reducing formula. So let me knock out those first two integrals first. That's 4 theta. And then over here, be careful, forget the -4. Antiderivative of sine theta is negative cosine theta, but then you have a -4 out here already, so it becomes +4 cosine theta. And then plus this right here, which is an integral, because I haven't taken the antiderivative. And then sine squared theta, I'm going to use that formula, the power reducing, and I have to double the angle. So just 2 theta here, d theta. And the 1/2 can come out. I'm going to go a little faster on this one because time. So I pull the 1/2 out. The antiderivative of 1 with respect to theta is just theta, but then there was a 1/2 in front. So 1/2 theta would be my next term. And then, let's try this. What's the antiderivative of cosine 2 theta? Well, that's going to be 1/2 sine 2 theta, because the antiderivative of cosine is sine, then I have to scale by the 1 over a. But in front of that, I had a negative sign, and I have a 1/2. So I'm going to put a negative and then a 1/2 in times, because it's multiplication there. And now that's going to become, when you put those two together, you get negative 1/4. So minus 1/4. Just got to be careful with that, the signs and stuff. And then plus c. We're done. Unless we can put some stuff together. We can put the thetas together. 4 theta and 1/2 of theta is what? I can't think right now. 9/2 theta, 9/2 theta. So 9/2 theta plus this minus that plus c. So everything there. This plus this minus that. That's your answer. Okay, that's number 8. Let's go with number 9. Number 9, sine squared cosine squared. Sine squared x cosine squared x dx. All right, so for this, they're both squared. Since they're both squared, I can't pull out anything like we did when one of them was odd. But this power reducing formula has been pretty effective. So what I'm going to do is I'm going to rewrite the integral. Rewrite the sine squared x first. That's 1/2 times 1 minus cosine 2x, because I doubled the angle. Then I rewrite this, and remember there's multiplication between them, so times 1/2, then 1 plus cosine 2x dx. Now, because this is all multiplication, the 1/2 times the 1/2 is a 1/4. I can bring that out. So I've taken care of those two. They're outside now. And then these two, I'm actually going to FOIL these out. 1 times 1 gives me 1. 1 times cosine 2x gives me cosine 2x. But then negative cosine 2x times 1 gives me negative cosine 2x. And those two cancel each other out. Nice. Then you have this times itself, a positive and a negative, so it's going to be minus that cosine of 2x, but because it was times itself, it's squared, dx. All right, can you find the antiderivative of 1? Yes, with respect to x, the antiderivative would be x. Can we find the antiderivative of this? Yes, but we'll have to use the power reducing formula again. So let me try this. Antiderivative of 1 is x, but I had a 1/4, so 1/4 x. And then, because I'm splitting this into two integrals, this 1/4 is going to come with us, and I'm going to put a minus here. So minus 1/4 integral, because I haven't taken the antiderivative, of cosine squared 2x dx. All right. So this one I took the antiderivative of, this one I have not. But then 1/4 had to come with me. All right, so now power reducing formula on that piece right there. So this becomes 1/4 x minus 1/4 integral, power reduce on that, 1/2, 1 plus cosine, double the angle, 4x dx. And we should be able to find the antiderivative of each of those individually. I'll have a 1/2 that comes out. So 1/4 minus 1/8, and then those two are taken care of. Let's find the antiderivative here. Antiderivative of 1 with respect to x is x. Antiderivative of cosine of 4x is going to be plus, because it's plus here. 1 over 4, because I have to scale by a, sine 4x. Parentheses. I use parentheses this time. Plus c. And then distribute the negative 1/8 through. So 1/4 x minus 1/8 x, and then distribute here to here, negative 1 over 32 sine 4x plus c. Put these two together, that's just 1/8 x minus 1/32 sine 4x plus c. What number was that? Was that 9? Yeah, that was 9. Oh no. Number 10, cosine to the 6th. That's a torture problem. I'm not willing to do that. Cosine to the 6th is just like cosine to the 4th, but you've got to apply the power reducing formula 3 times. I would never ask you to do that on a test. That's just, like I said, that's just tedious. I encourage you to do it because it really helps you with keeping track of signs. And I've done it many times. I've done cosine to the 6th, I've done sine to the 6th, I've done cosine to the 8th, and I've done sine to the 8th. In those you have to take it and do it like 4 times. It's even worse. And it actually turns out the times that I've done it in the past, here's my sheet of paper. I actually had to turn my paper landscape sideways to get it all to fit in because it was just such a disaster. But I'm not willing to do it here. To me, that would just be a waste of time. So there's nothing new in that problem. 3 applications of the formula. Lots of numbers to keep track of, constants to keep track of. But you'll be okay without seeing it, I hope. Number 11. T sine squared t dt. Integral t sine squared t dt. Okay, so this doesn't look like anything that we've done up to this point. Because you have a sine squared there, but you also have a t there. That t is not a trig function. And so what we've done in the past doesn't appear that it would work because of the t. So we need to kind of rethink this. Maybe there's something else we can do. So I'm looking at that and I'm thinking, okay, well wait, with integration by parts, if I pick like this to be u, the derivative of that is just going to be 1. And that's good because in my new integral the t will be gone. The problem with that though is that this would have to be dv and I have to be able to integrate it. So let me kind of explain what I'm thinking here. I'm thinking I'm going to let u be t because du is dt and that's nice. Here though I would have to let everything else be dv, which would be the sine squared t dt. And now I've got to figure out what v is, so I've got to go up here on my table, which means I have to integrate that. And that's not an easy integral just that we know mentally. So what I'm going to do is on the side, I'm going to ask myself, can I even integrate that? Can I integrate sine squared t dt? Of course we can. We just did this problem. We use the power reducing formula. We get a 1/2 that comes out. We get 1 minus cosine, in this case 2t dt. So using the power reducing formula, remember the 1/2, I just pulled it out now. I can find the antiderivative of each of these, no problem, and then distribute a 1/2 through. So 1/2, antiderivative 1 with respect to t is t. Antiderivative of this will be, let's see, antiderivative of that is just 1/2 sine 2t. But then I come in here and make it negative 1/2 sine 2t, and then I hit it with a 1/2. So it becomes minus 1/4 sine 2t. That's the antiderivative plus a constant. But I'm not going to do that until I put this all together. I'll throw the constant at the very end. So that's the antiderivative of sine squared. So look what we've done here. Integration by parts used to work for us because this became easier and this was something we could do pretty easily. Now you can see that this step going up might actually require some work. So that's okay, that's what we have. So this equals this answer, 1/2 t minus 1/4 sine 2t. And now when I look at setting up my ultraviolet minus voodoo, right? Voodoo, my diagonal here, is just going to be that new integral is going to be this times dt. But wait a minute, That just means I have to integrate this again, but that's an easy one to integrate. Antiderivative of this is straightforward, antiderivative of this is straightforward. So I'm in business. This answer will be ultraviolet, this times this. So how are we going to do that? Because this is two terms. Well, I just distribute the t to each one. So it'll be t squared, 1/2 t squared, because it had a 1/2 on it. So 1/2 t squared minus 1/4, then I'll bring that t in right here, t sine 2t, now minus integral of voodoo, which is this across. So 1/2 t minus 1/4 sine 2t dt. I guess I'm going to need all this space. Okay, I've got about 20 minutes the most, maybe about 15. About 15. Okay, so let's go ahead and integrate that now. So we have 1/2 t squared minus 1/4 t sine 2t, and then antiderivative of this. So cover up the 1/2. That antiderivative of t is 1/2 t squared, but then you hit it with a 1/2, it becomes 1/4 t squared, and then minus. So minus 1/4 t squared. And then, this is going to get a little complicated, but antiderivative of the sine of 2t is negative 1/2 cosine 2t. You hit that with a negative 1/4, that becomes positive 1/8, and then you hit it with a negative again. So minus 1/8 cosine 2t plus now my constant of integration. And we can put the 1/2 t squared minus 1/4 t squared, that just becomes a positive 1/4 t squared. And then all of that. All right, what number was that? 11? I'm actually going to look at this one in the book. See if it looks the same. 1/4 t squared minus 1/4 t sine 2t minus 1/8 cosine 2t. All right, looks good. All right, what's next? 12. I think I'll skip 12. 12 is exactly like 11, except they use cosine squared instead of sine squared. So I'll skip 12. 13 looks interesting. I may have done 13 in class now I think about it. But this will be the last one I do on this video because I've got to pack up and get to my meeting. And this video is coming right on an hour here in just a minute, in just about 10 minutes, so that'd be good. So number 13. Cosine squared x, tangent cubed x. All right, so again, this does not fall into the category that we had earlier because we needed sines and cosines together if we were going to use any of those methods. Here we have cosine and tangent. But let's just remember that tangent is sine and cosine combined. So this is cosine squared x times tangent of x is sine x over cosine x. So this is sine cubed x over cosine cubed x dx. That's what tangent cubed means. And that's actually going to cancel out here. Those two cosines cancel with two of the factors of cosine, so I still have one factor of cosine there. So I have integral, let me write it this way, sine cubed x over cosine x dx. And now you look at that and you're like, well, what do I do with that? Because what you can't do is what we've done in the past, because the cosine is in the bottom. So you can't be looking at that as, oh, I've got cosine to an odd power. It's actually cosine to the negative one because it comes up like that. But let's just see. Maybe there's still a way we can do it. I know that the derivative of cosine is sine. I know the derivative of sine is cosine. I don't want to choose sine to be my u because the derivative of that's down here. So I'm thinking basic substitution here. If I choose u to be cosine, the derivative of it's up here, but then it's cubed, and I told you to avoid that. You want to avoid your derivative being trapped somewhere. But maybe there's still a way I can do it. So this is where things start to get real weird, because it's like now you're going to do something I told you to avoid. But you just got to kind of take swings at this thing and hope that things work out. If not, your other option is to not even try, which isn't an option, right? So I'm going to peel off one sign because I know the derivative of cosine is negative sine. So that'll give me my du. I just need to resolve the sine squared. But sine squared is 1 minus cosine squared. So that top is 1 minus cosine squared x over cosine x, and then sine x dx. And now I've got everything over here in terms of cosine, which is going to be my u, and the derivative of it is out here, basically. I'm off by sine, but I'm going to let u be cosine x. Du is negative sine x dx. Negative du is sine x dx. So let's rewrite this integral. Integral 1 minus u squared over cosine of x was u. Then sine x dx is negative du. So here's du. Here's your minus. Very good. Now, because I have a single term in the denominator and 2 on top, I'm going to just split this into 2 fractions. It'll be 1 over u, and then the other one minus u squared over u, which is just u, and then du. And I'm going to do what I did earlier. I don't like the negative out here if I've got 2 terms, so I'm going to distribute it. It's going to make this negative and that positive. So I'll switch the order. I'll put the u first as positive, and then minus 1 over u, du. And now just antiderivative of that. So antiderivative of u by itself is 1/2 u squared. And then the antiderivative of 1 over u is natural log of the absolute value of u plus a constant. And now all I have to do is go and replace u. And this answer is really strange because if you remember what we started with, look at what our answer is. U is cosine x, and I'm squaring it, and then minus natural log of cosine x plus c. So our original integrand was what, like sine cube? No, sine cube? What was it? Oh, cosine squared tangent cubed. It was cosine squared tangent cubed. And our answer has natural log in it. It's kind of strange. All right, but that's it. So I believe that is going to be all I can do right now, time-wise. And that'll be it. Yeah, I'm getting a text. It's probably that I need to get to this meeting. All right, I'll see y'all again soon. Okay, I'm back here to do some more problems from this section on trig integrals and trig substitution. So let's see here. Where did I leave off? What did I do last? I forgot what I did last. I think I did number 13. Yeah, I did 13. So let's look at 14. 14, integral, let's see, cotangent to the fifth theta, sine to the fourth theta, d theta. All right, so again on this one, it's kind of like the previous problem that we did. We don't have sine and cosine explicitly here. So what I'm going to need to do is first rewrite this cotangent. So I'll go ahead and rewrite the cotangent as, cotangent, remember, is the reciprocal of tangent. Tangent is sine over cosine. So this is going to be cosine to the fifth theta over sine to the fifth theta. And then I have sine to the fourth theta d theta. And I get 4 of my factors of sine to cancel out, which leaves me 1 factor of sine here, which leaves me integral cosine to the fifth theta over sine theta d theta. And just like the previous problem, I'm trying to find which of these to choose as my u. I don't want to choose cosine as my u because du is in the denominator. That's hard to deal with. But if I choose my u to be sine theta, the derivative is up here, and I can split one of these cosines off to make the derivative appear over here. So I'm going to rewrite the integral first and peel off 1 factor of cosine. And now you can see here I've got u and there's du. So my substitution here is u is sine theta, du is cosine theta, d theta. I have that exactly right here. So I'm going to replace that with u, that with du, and now I need to get this taken care of, the cosine of the fourth. And I can use this substitution here. I need to get this in terms of sine. So all we do now is just rewrite cosine using the Pythagorean identity. Since I have cosine to the fourth, an even power of cosine, that's a good thing, because I can write it as cosine squared. So this will be equal to integral cosine squared theta squared over sine theta and then cosine theta d theta. And remember that cosine squared theta is 1 minus sine squared theta. So you have 1 minus sine squared theta squared over sine theta cosine theta d theta. So we're making good progress here. Now I've got all the stuff over here has sine in it, which means I can replace them with u's, and cosine theta d theta is my du. So now rewriting this integral, I have 1 minus u squared squared over u and then du. And at this point what I can do is expand out the numerator. This will become 1 minus 2u squared plus u to the fourth on top over u. I really don't need the parentheses here. Okay, and then du, like that. And now I have 1 term in the denominator, 3 terms in the numerator. I can split this up into 3 separate fractions and use the power rule on 2 of them, and on 1 of them it's going to be a natural log when I take the antiderivative. So this becomes integral, okay, first one, 1 over u, and then minus 2, and then u squared over u is just u, and then plus u to the fourth over u is u cubed, du. And now I just take the antiderivative of each of these. So antiderivative of 1 over u is natural log absolute value of u, minus, okay, antiderivative of u is 1/2 u squared, but then I had a 2 here. The 2 and the 1/2 just go away, so I get u squared. And then the antiderivative here is 1/4 u to the fourth, then plus my constant. And now I'm going to come in here and replace all my u's with sine theta. So natural log sine theta, and then minus sine theta, but I'm squaring it, plus 1/4 sine theta, but I'm raising it to the 4th, and then plus c. And that should do it. Let's move on to number 15. All right, so 15, 1 minus sine x over cosine x. Over cosine x dx. Well, initially, I see I can split it in two fractions because I have 1 over cosine, sine over cosine. Let me just write that down. That would be 1 over cosine x minus sine x over cosine x dx. 1 over cosine is secant x minus sine over cosine, which is tangent x dx. And then remembering that our formula sheet does actually have the antiderivatives for all of the trig functions that are just by themselves. So like the antiderivative of secant is number 14 on the formula sheet, and antiderivative of tangent is number 12. So I can go straight to a formula here. These are all equal. This is equal to, okay, the antiderivative of secant is going to be natural log absolute value secant x plus tangent x, and then minus the antiderivative of tangent x, which is natural log of secant x. Now, there are other ways you can do this problem, but I think that's probably the easiest way. So I'll stick with the easy way. All right, let's look at number 16. I like them when they're nice and easy like that. Just remember, if you have an integral with sine, cosine, tangent, secant, cosecant, or cotangent, all of those have formulas. So if we get them where they're just by themselves, we're happy campers. All right, cosine squared x, sine 2x. All right, so remember this is sine 2x like this, like in parentheses. All right, so we can't work with those together right now because the argument here is x, the argument here is 2x. We either need them to both be x's or both 2x's. So I'm going to go and just use my double angle identity from pre-cal and rewrite sine 2x as 2 times sine x times cosine x dx. I'm going to pull the 2 out of the integral and put the cosine and cosine together, get cosine cubed x times sine x dx. And this one is pretty straightforward because we got sines and cosines together. They're actually both to an odd power. I'm going to go ahead and choose my u to be cosine because that'll become u cubed, and then this is the derivative of cosine. I'm off by a sign. So u is going to be cosine x, du is negative sine x dx. Move that negative over, and then I'll just rewrite the problem. This is equal to, I had a 2 out here. Cosine x is u, so u cubed, and then sine x dx is negative du. Here's my du, here's my negative, so it's going to change it to a negative 2. And it doesn't get much easier than that. The antiderivative there, I have a negative 2 out front. Antiderivative of u cubed is 1/4 u to the 4th plus a constant, and remember u is cosine. So put these together, negative 1/2 cosine to the 4th x plus c. That's it. This is your answer right here. 17. It's a long homework assignment. All right, tangent x, secant cubed x. Tangent x, secant cubed x dx. Now, this is where we're moving into a different sort of strategy, because if we have sines and cosines, we'll do certain things. But if we see secants and tangents, we do something else. So in your notes, I believe I gave you something on the strategy for this. Let me see. So if the power of secant is even, we're going to do a certain thing. Here the power of secant's not even. If the power of tangent is odd, which it is because it's 1, then we do something else. And this is what we do. Tangent of power is odd. We save a factor of secant tangent and use a Pythagorean identity. Our u substitution is u is secant x. So let me just write down the substitution first. That's going to be our substitution. And let's see why that substitution is going to work. The derivative of secant x is secant x tangent x dx. And so what I'm looking for is to try and get a secant x tangent x out of this. So notice that if I take the tangent x out over here and peel one secant off of that, I get secant squared x times secant x tangent x. So I'm just rewriting the integral, right? This is still secant cubed, and then here's tangent. But notice that secant x tangent x dx is du right here. So that means that I've got to come in here with what's left and somehow get that in terms of secant, which it already is. So this is going to be straight away, u is going to be secant x, so u squared. Then everything out there is du. The antiderivative here is 1/3 u cubed plus c, which is 1/3 secant cubed x plus c. So that's it. Let's take a look at the next one. Tangent squared secant to the 4th. Number 18. Tangent squared secant to the 4th. So with this one, my tangent is not odd. My secant, however, is even. So when we have an even secant, the strategy is to peel off a secant squared. So I'm gonna peel off a secant squared, and I'm gonna let u be tangent x. So u is tangent x. The derivative of tangent x is secant squared x dx. So remember, the idea was peel off a secant squared, because if this is even, you're definitely going to have a secant squared. So this will become integral tangent squared x times secant squared x times secant squared x dx. That's multiplication. So I've peeled off a secant squared x dx, and that's because this matches up here. So I've got du right there. I can replace my tangent with u, so this will become u squared. But what about the secant squared? I don't call it du again because this is du. I would need the dx there with it. So I need to somehow rewrite this in terms of tangent. So you got to go back and remember some Pythagorean identities. 1 plus tangent squared x equals secant squared x. That's Pythagorean identity. And so if I want to know what secant squared x is, here it is. And that's in terms of tangent. So what I'll do is I'll come over here. I'll leave tangent squared x alone out here. I'll replace secant squared x with 1 plus tangent squared x. Have to have it in parentheses because it's two terms, and that tangent would distribute if we multiplied that. Secant squared x dx. So there's my du. Here's u squared. Here's 1 plus u squared. So I can go directly to my substitution now. u squared, 1 plus u squared du. Then distribute my u squared through. U squared plus u to the fourth du. And then power rule. 1/3 u cubed plus 1/5 u to the fifth plus c. And then replace our u's with tangent x. So 1/3 tangent x, but cubed, plus 1/5 tangent x to the fifth plus c. And that's our answer. So showing you two different strategies when you have tangent and secants together. All right, let's look at 19. Tangent squared x dx. So if that was just tangent, you would just go to your formula, because we have formula when the trig function's by itself. Of course, you can't put it tangent, tangent, and then do each one, because that would be like breaking the rules of products. You can't integrate products by just integrating them separately. So I don't know what the antiderivative of tangent squared is. That's what we're trying to figure out. But I do know this, going back to this identity, the Pythagorean identity, 1 plus tangent squared x equals secant squared x, that if I move the 1 over, just subtracting it on both sides, that I can rewrite it this way. Now, what's the advantage of that? Well, the advantage is that with these two terms, I actually do know the antiderivative of secant squared, because in Cal 1, I learned that the derivative of tangent was secant squared x. So the antiderivative from this should just go back up to tangent. And then, of course, the antiderivative of 1 with respect to x is just x. So integrating both of those separately, you get that. And that's it. We're done. Let's check it real quick. We haven't checked many of these. What's the derivative of this? Secant squared x. What's the derivative of that? Minus 1. And what's secant squared x minus 1? It's tangent squared x. So it works. 20. Tangent squared x plus tangent to the fourth x. Tangent squared x plus tangent to the fourth x dx. Well, I could split this up into two. I could split this up into two because I have two terms, and I know the antiderivative of tangent squared x. I just did that problem. But tangent to the fourth is a little different because I can't use the Pythagorean identity with that one the way I did the other one. The reason being that I can replace tangent squared x with secant squared x minus 1. I can do that, but if this was to the fourth power, then this would be the same as squaring this, and that would mean square that, and then you'd have to expand that out, and that does not look fun. But let me just try some things here. Let me factor out a greatest common factor. Tangent squared x is a common factor. Get 1 plus tangent squared x here. So if I distribute this, I get that. But wait a minute. Tangent squared x plus 1 is secant squared x. Maybe this will help. Tangent squared x times secant squared x dx. So just replacing this with secant squared x. And now I have a tangent and secant appearing together. I've got an even power on secant. Whenever that happens, I let u be tangent x. The derivative of that is secant squared x dx. I have secant squared x dx. I just need to make sure I rewrite this. But u is tangent. So this is just going to be integral u squared du. That's it. And then the antiderivative there is 1/3 u cubed plus c, which will be 1/3 tangent x cubed plus c. That's it. We're good to go. Kind of weird that it works that way, but it does. All right, let's look at 21. Tangent to the fourth, secant to the sixth. This does not look fun. Tangent to the fourth, x, theta, what is it, x? Secant to the sixth x dx. So you have tangents and secants appearing together. Your secant is to an even power, and because of that, you're going to peel off a secant squared. U will be equal to tangent x. Du will be equal to secant squared x dx. Let me try this. Integral tangent to the fourth x. Let's see, I'm peeling off a secant squared x, which leaves me with a secant to the fourth x. That's du right there. My tangent can be replaced with u, so that's u to the fourth. So what about secant to the fourth? I've got to figure out what that is. Now hold on, I'm getting a text. Let me just check out what this is. Let me find him. Where is he?
I'm
Hey,
sorry.
come on.
He was in there recording a lecture. I know where to find you.
Yeah, I was trying to get something done. How's it going?
Good, how are you, sir?
Come in real quick.
Sorry to interrupt.
No, it's okay. Let me finish this problem out. Just have a seat. All right. Okay, so we've got to deal with the secant to the fourth. So going back again, we had said by the Pythagorean identity, secant squared x is 1 plus tangent squared x. And so if this is to the fourth, we can say that that's that squared, and then that means it's that squared. So what I'll do is I'll replace secant to the fourth x, which is this, with that. So we've got integral tangent to the fourth x, and then in parentheses, 1 plus tangent squared x, but then that quantity squared, and then secant squared x dx. And now I make my substitution. U is tangent. So when I make the substitution, I've got integral u to the fourth, 1 plus u squared squared, and then that's du. And that one right there we should be able to handle because it's polynomial. So we're just going to go now and let's expand this out. So integral u to the fourth, and then we get 1 plus 2u squared plus u to the fourth. And then we distribute this through. So u to the fourth plus 2u to the sixth plus u to the eighth. And now we're there. Power rule. 1/5 u to the fifth. Let's see, plus 2/7 u to the seventh plus 1/9 u to the ninth plus a constant. And now final step is replace all your u's with tangent x. So we have 1/5 tangent x to the fifth plus 2/7 tangent x to the seventh plus 1/9 tangent x to the ninth plus a constant. That's it. That was it. All right, let me pause it. So I'm not going to pick up where I left off, because I think I left off doing like number 21, I think was the last one I did, but I'm going to start doing some trig sublins. So like number 40, where should I start? 40, 39? Is that the first problem that I assigned you?
Which?
Out of the homework, out of the textbook? 39?
Problems were 1 through 27 out and 39 through 60.
Yeah, 39 through 60 something. So let's do that. All right. Come on, Kiki. Again, here we go. Do y'all have that cheat sheet thing I gave y'all? The one, yeah. Oh, you know what? You want one of these? Yeah, this is a new one. This is a different one. Okay. All right, so I'm doing number 39. I'm going to make sure I have this written down right. So just to be clear, out of the homework, out of the book, I told you to do what? 1 through? But the ones before that, 1 through what? 1 through 27. So I still have a couple to do there. I haven't done those yet. All right, who cares? I'll come back to those if I have time. 39, integral dx on top, but I like to always peel my dx off the side. The book always puts dx on top, and I think they do that to save room so they don't have to go as wide, or just to give you some variation. So we look at that, and what are you thinking? I mean, it's obvious because we know what section we're in, right? But what are you thinking? See the square root there? You've got a number minus something squared, your variable squared, which fits into. So this, according to this, we should make a substitution. I'm using the format that looks like this. Square root, what is my constant squared first, then minus my variable squared. So according to this, I should make the substitution x is equal to a sine theta, which for us in our problem, what's a? A is 2, right? So a for us is 2, right? 2 squared, and that means our x substitution is going to be 2 sine theta. So what do you do once you have that? Once you know what your substitution is going to be, remember there were 3 things now you go get? We'll figure out what the root is. Let's do the derivative first. Okay, so let's take the derivative of this first. The derivative of this is 2 cosine theta d theta, right, Zach? And now I have to get the root part, right? So I need to rewrite this root. And this is the part that some people were getting stuck on in class. Okay. This is equal to the square root of 4 minus what? If we rewrite x, so it's 2 sine theta, but squared, right? So what happens? You get 4 sine squared theta. And then what can you do here? Take a 4 out. You okay with that, Zach? And then what is this? Cosine squared theta. So this is equal to square root of 4 cosine squared theta. And that's what makes the trig substitution so good, is because you wind up at the end taking that complicated expression and rewriting it as a pretty simple trig expression. Right? 2 cosine theta. And so these are the 3 things. So I think I numbered them in class. 1, 2, and then 3. This equals this. And then you go and you just rewrite the whole problem. So let's go ahead and rewrite it. Any questions? All right. Integral. All right. 1, I'll do that part. 1 over. Do y'all care if I ask you? No? Zach?
Should be
So the x squared is actually going to be what instead of 2 sine theta, but then squared. So that's what? 4 sine squared theta. Good. So that's what x squared is. Times 2 cosine theta, because that's what the root is. And don't ever forget dx, which is 2 cosine theta. D theta. Yeah. And some things actually happen pretty good here. That cancels completely, and the 2, right? And so I have a 4 on the bottom that I can take out of the integral as a 1/4. The integral, I've got 1 over sine squared theta d theta. That's all, right? Any ideas on what to do with that? Good that you're thinking that, except for the fact that the sine squared is in a denominator. If it was on top, I totally agree. That's what we would do. But because it's in the denominator, can't really get away with that. Because it'll split it into 2 terms, but then you can't split it into 2 fractions, because 2 on the bottom, 1 on the top. Makes sense? It would actually probably make it a little bit worse.
So what have you compared it to the Pythagorean identity?
Like 1 minus cosine?
Yeah.
You could do that. I think you're going to be in the same boat, though, because
It'll be negative, you can bring the negative out, and it'll be 1 over cosine, which would just be secant.
you would have 1 minus cosine theta here, right?
Bottom.
2 terms, though. So that, again, you'd be stuck with that 1. What is 1 over sine theta? Cosecant? So isn't this cosecant squared? And now just go back and think about this for a second. Wasn't,
Formula 9.
yeah. Wasn't there something in Cal 1, the derivative of tangent was secant squared, the derivative of cotangent was negative cosecant squared. So going backwards, the antiderivative of this should be negative cotangent theta. But then we have a 1/4. So this is straight up, what formula did you say it was?
Formula number 9.
Formula number 9. There we go. Now we have to go back to x.
Reference triangles once you get back to x.
Yeah. Now reference triangles. So now I'm going to come over here, and I'm going to write down the information I have that connects x and theta together, which is always going to be your first substitution, the one that you got from the very beginning, which was x was 2 sine theta, right? Wasn't that it? Yeah, I'm pretty sure it's what we put. Yeah, it is. And then divide by 2 on both sides to create the ratio, and then draw your triangle based on this. A lot of times you'll see when I do these problems, a lot of times I draw my triangle even if I don't even need it. Like even if the problem doesn't require it, just to keep practicing this over and over and over. So which sides get labeled here? Two's the hypotenuse, opposite, and then that forces this side to be the square root, 4 minus x squared. And remember also I said that one of the sides will always be that square root thing that you had. All right. What is the definition of cotangent? It's the reciprocal of, so it's cosine over sine? Or adjacent over opposite, right? Adjacent over opposite. So this is going to become negative 1/4 times the adjacent side of this triangle over the opposite side. So root 4 minus x squared over the opposite side x plus some constant of integration. That's it. All right. We satisfied with that, or want to check it, or satisfied?
Check it since it's the first one.
You want to check it?
Since it's the first.
Okay, since it's the first one, we'll check it. All right. Okay, so I need to be able to take the derivative of this, right? So let's just not even deal with the negative 1/4 for right now. Let's just come back to that. Let's take derivative of this. So I have square root 4 minus x squared over x. I'm going to take its derivative, which means I'm going to use the quotient rule. The derivative of the top comes first. The derivative of the square root of something is 1 over 2 times the square root of that something. But because there's something inside of it, I have to do chain rule, which means derivative of the inside, which is negative 2x. That's the derivative of the top. Times the bottom, then minus the derivative of the bottom, which is 1, times the top, which is this. All of this over the bottom squared. And now at this point, I'm going to clean up the numerator. All right, so I have the negative 2, or the 2 here cancel. X times x is x squared. I have a negative. So I have negative x squared over root 4 minus x squared minus root 4 minus x squared. All of this over x. Not yet, they don't cancel because there's subtraction. If it was multiplication, yes. But I would have to put these together with a common denominator. Like if I want to combine these two together, so imagine that that's over 1, I would then have to multiply this top and bottom by what? Square root 4 minus x squared over square root 4 minus x squared. Now they would have the same denominator. So what I get is I have the negative x squared, which is this. This root times this root, the roots go away, and you just get 4 minus x squared. But it's subtraction. So it's actually minus 4 plus x squared. All over, oh, wait, hold on. This right here, x, was supposed to be squared, right? Sorry. All over the common denominator, which is this. All over what? X squared. These x squareds cancel, right? Or they add and they're gone. So then I have negative 4 over square root 4 minus x squared, all over still what? X squared, and I can look at x squared as being x squared over 1, and then flip it, and when I flip it I can put it in the back or the front. I'll just put it in the front here as x squared, and then a 1 up here, but I don't need that 1, right? I don't need to write the 1 up there, which is this. And then what was that constant I said to forget about? We'll just bring it in at the end. Okay. It was negative 1/4, wasn't it? So if you multiply this times negative 1/4, the negative and negative become positive, and then the 4 goes away, and you just have 1 over x squared root 4 minus x squared, which is the original problem, the original integrand. So it works, it checks out. Cool. All right. So I said 39 through what? Odds or no?
61 odd.
Odd, okay, I guess I'll just do the odds then. All right, 41. Square root x squared minus 4 over x dx. So you're thinking trig sub here again? What format do we have here for this? X squared minus a squared. We have the format square root x squared minus a squared, which according to this, I need to make the substitution x is equal to a secant theta. A for us in this problem would be what? 2. And so I'm going to make a substitution, x is equal to 2 secant theta. If I do this, things should all work out real nice. All right, so let's write down the 3 things that I said we'll need. X is 2 secant theta. Dx would be next, right? That'll be 2, and then the derivative of secant theta, which is secant theta tangent theta d theta. And then the square root thing we need to write, which I didn't write down what it is, but I think it's obvious what it is, right? It's the x squared minus 4. Square root of x squared minus 4 will be square root of, let's see, you want to do this one, Kiki?
4 secant squared theta
4 secant squared theta
minus 4.
minus 4, and that's using this, just squaring that.
And you take the 4 out and it becomes secant squared minus 1, which equals tangent squared.
Yep, this is,
4 tangent squared. Once you take it out of the root, then it's 2 tangent.
okay, good. So taking out the 4, you're left with this. That's a Pythagorean identity. That is tangent squared theta. And then square root of each one, you get 2 tan theta. 2 tan theta. So using that information, we should be able to rewrite the entire integral. And then at that point, it's a trig integral, and we try and do whatever. And do you see why we studied sine and cosine ones first, and then we studied tangent and secant ones next? See, this substitution requires secants and tangents, so we need to be able to handle this once it's all written out again. You know what I'm saying or not? I mean, we didn't deal with integrals that have like sine and cosecant in it. Like, why not? Because of the trig substitutions, the ones that you get at the end are usually sine and cosine or secants and tangents. So those are the 2 types we spent a lot of time on.
Sine and cosecant, you still break down into sine and cosine.
You could.
Yes, you could do that.
You could. We just like when it's secant and tangent, we like to use the fact that the derivatives of those are connected to each other. So,
Parallels, but not parallels anymore.
yeah. All right, so what's the numerator going to be? 2 tan theta over 2 secant theta. And then 2 secant theta tangent theta d theta. You see how important this dx is? I mean, we have to convert it to what it is, right? Which kind of created a little bit of an issue for us, but we should be able to handle this now. Secants cancel, 2's cancel. The 2 that's left can come out. Integral, then what? Tan squared theta. Is that all right like that? And then how do we integrate tan squared? Pythagorean identity? What do you mean? Secant squared minus 1. Good. And you would rather deal with that one? Why would you rather deal with that? That's right. Exactly, because you know the antiderivative of this and you know the antiderivative of 1. Perfect. Good. All right. So, Kiki, you with us? Okay. So let's go ahead and take the antiderivatives now. We have 2, and then antiderivative of secant squared theta is just tangent theta, and the antiderivative of 1 is theta in this problem, because theta is the variable we're integrating with respect to. And that's our answer. But we need to get it back to x now, don't we? Was it x? I'm going to distribute the 2. I didn't have to. I don't know why. I just didn't like it sitting out there all lonely. reference triangle. I don't even know if I'll need it. I'm going to draw it anyway. So the information that I had was that x was 2 secant theta, right? X was 2 secant theta, which meant that x over 2 was secant theta, which meant if I draw a triangle, secant is the reciprocal of cosine, isn't it? So what side is which here?
X is on the hypotenuse and 2 is on the adjacent.
X is hypotenuse, 2 is adjacent. Do you agree? And that forces this other side to be this squared minus this squared, which better matched that root that you had earlier, which is, that's the root that started this whole thing off, right? All right, so we need tangent, right? We need tangent of theta over here. So 2 times tangent of theta is opposite over adjacent. So root x squared minus 4 over 2. That's nice. And then minus 2 times, theta. So how are you going to get theta?
Solve the theta
Where?
where x is equal since you're going back to x.
Okay, we can use this, or we can use this. Which one is going to be the one that we can get theta isolated from? Because you can't divide just SEC, those letters, right? You can't just divide that out. Arc, it would be the inverse secant function. So you're going to do arc secant or inverse secant on both sides. So if I take inverse secant on the left side, and I do inverse secant on the right side, it just gives me theta. And so that's what theta is. In terms of x, that's what it is. So that's what I put here. Secant inverse x over 2 plus c. We studied, in the very beginning, we studied the inverse trig functions and their derivatives. So if you go to your derivative formulas, you should have the derivative of that. Oh, hold on a second. Oh yeah, I was just saying that if we wanted to check this, which I'm not going to, you could look up the derivative of secant inverse, which is on there, and so we would have a way of differentiating that if we had to. These two's cancel. So, all right. Catching on to this? Yeah?
Yeah, I think I missed last time in this lecture.
You missed this lecture? Yeah.
Threw me off
Yeah.
completely.
What's the only difference with what it's had a trig in the answer? Everything else
That's right. Yep. And that's always going to happen if one of your things at the end here is theta. Just theta. Then when you go back to get x, you're going to have to use a trig function, an inverse trig function to get it back.
So in the answer, would you want it just left as is, or do you want the numerical value?
No, well, we don't know it because we don't know what x is,
Okay.
right? So we wouldn't be able to. No. All right, 43. Integral 1. This looks very similar to one we just did. T cubed square root t squared minus 1. Oh, no, it's not similar, is it? It's similar to 39. We had x squared, but then inside we had, I think, 4 minus x squared. Here it's a different, we're going to use a different substitution. And it's cubed here, not x squared. So what's the, let's see if we can do the actual substitution without having to write all that stuff down. Just say, what is the substitution going to be?
A would be square root of that.
A is the square root of 1, which is 1, right? So A is 1 here. So what substitution are we going to use according to this?
1 secant.
1 secant theta, right? 1 secant theta. So we're using the fact that we have the square root of the variable squared minus a constant squared. Now keep in mind, in the formula they use x, right? Here it's t. So we're not going to say x equals. We're going to say t equals. T equals 1 secant theta. This is 43, yeah. And then from here we differentiate. dt equals secant theta tangent theta. d theta. And then the square root part of this, t squared minus 1 equals, since we just did this, yeah, it's going to be just tangent theta, right? If you go through it. If I replace this with secant theta, secant squared theta minus 1 is exactly tangent squared theta and then square root. So tan theta. Is that all right, everyone? If you look on that formula sheet that I gave last semester, don't I tell you what the square root is? Yes, I do. I'm not telling them. Yeah. I'm going to tell them today. I'm going to allow them to add it to their formula sheet, but I wanted them to at least try some of the homework where they had to get this every single time.
So I believe you allowed us to add this along with the formula sheet.
Yeah.
I don't know about this.
Yeah, I don't know either. I don't really like this group that I've got. I'm kidding. Right, Kiki?
You're only saying that because you're on camera.
Did I turn my thing back on? Yeah. All right. Rewrite everything, right? 1 over secant cubed theta times tangent theta times
Secant tangent.
secant tangent. Okay, so
We'll leave you with 1 over secant squared.
1 over secant squared. Okay, I think you might finally get your wish here, Kiki.
What wish is that?
What you wanted to do earlier that you weren't able to do.
Which problem?
You'll see. Is that right? You're gonna have 1 over
1
secant squared.
And then it's going to be 1 over 1. No.
What is secant squared? What is secant? Sorry, what is 1 over secant the same as?
Cosine.
Cosine. So everyone's good with that, right? Okay. So this is really just 1 over secant's the same as cosine. So this is just cosine squared. You see what I'm saying now, Kiki? That's cosine squared theta. And now you can use that half angle or power reducing formula, whatever you want to call it. How many of you like that formula being called the half angle formula? I think that's what it's on the sheet, right? Isn't that what it says?
Reducing.
I'm talking about the one that's formula that says cosine squared x equals 1/2 times 1 plus cosine 2x. They call it half angle. I've never liked this being called the half angle identity. I don't know why, but I've never liked it.
Do you have a better one for it?
Power reducing. Because where is the half angle of that name coming
It's
from
because
here?
there's a half there, I'm pretty sure. Someone's like, let's just call it that.
Half angle, though, would to me imply half the angle. So what? Yeah. So I see. I understand why they're doing it, because here you have twice the angle, right? And in this side of the equation, it's half of that. So this is a way to relate this together, where you have double the angle or half the angle, half of that. But to me, this formula allows you to reduce the power. That, to me, is the key. You reduce the power from square down to linear. Yes, you double the angle in the process. But halving, I don't know, I just don't like it. So I'm going to continue to call it power reducing. And I didn't make that up. Some books, they do refer to it as the power reducing formula. So rewriting cosine squared theta as 1/2 times 1 plus cosine 2 theta, doubling that angle.
Just take the 1/2 out.
Take the 1/2 out, and then we'll be ready to integrate, won't we? So the 1/2's coming out. Integral of 1 plus cosine 2 theta d theta I could do integration all day long. I could just do this for 8 hours straight. Like that. Clock in, do integrals for 8 hours, clock out.
You already do.
Yeah, but not for 8 hours. I'm just saying I could if I had. I would enjoy that.
3 hours, 205 hours of lecture, you sure?
You know, I haven't lately. Now it's starting to be more like that. But okay, so what's my antiderivative here now?
1/2 theta plus 1/2 sine 2 theta.
Okay, so Zach, as soon as you see that theta, you're already thinking what?
That I have to remember to swap out theta after the reference term.
Yeah, so you're going to have some trig stuff. You noticed that, right? Or who said that?
You did.
Yeah, but I thought you were the one who pointed it out. Like you're always going to have a trig. Yeah, okay, that was the first one. Well, now that we see that, we know we're going to have a trig, an inverse trig in our answer somewhere. And then the antiderivative, be careful on this one. The antiderivative of cosine 2 theta is 1/2 sine 2 theta, right? Because you always have to scale out the a here.
Is that the 1/8?
That's the 1 over a right there. And then the 1/2 I'm just keeping out here. When it distributes through, it'll become a 1/4,
Okay.
right? 1/2 theta plus 1/4 sine 2 theta plus c. Now, again, because it's just in my nature to want to draw the reference triangle, I'm going to do that. I think I'll put it up here. We had t, right? Not x. T was equal to secant theta. And that means that I can draw it right now, can't I? Remember, t is like t over 1. That's create your fraction that way because you don't have a number to divide through by. Secant's the reciprocal of cosine. So hypotenuse is t. Adjacent's 1. Opposite square root t squared minus 1.
And then shouldn't you get your, shouldn't you go ahead and get your theta?
Yeah, you want to get theta now? Sure, I'll get it right here. Secant inverse t equals theta. So take the arc secant on both sides, or inverse secant. That's already noon. What about this though? We can't use that triangle on this. Why? It's 2 theta. You can only use, this triangle only works for trig functions of theta, not of 2 theta. But, what do we know about sine 2 theta?
Isn't that just sine theta, cosine theta?
2 sine theta, cosine theta, yes, correct. So going back, the pre-cal formula, this is called the double angle identity.
Do you not like that one either?
No, that one makes sense to me. Because it is a formula that involves the double angle, right? If this just so happened to be cosine of 2 theta, would you still be able to do something like this? Not exactly, but is there a formula for cosine 2 theta? There is. It's in the double angle identities. There's actually 3 equivalent versions of it,
Tangent.
right? And tangent, right? So you can handle any double angle. Now, what if this was a triple? You're stuck. You'd be stuck. You'd be stuck. But that would never happen because the way we got 2 theta was using the power reducing formula, which always doubles your angle. So you would never get a triple in there, if that makes
So
sense.
if it was 4, you have it squared.
Yeah. If this was 4, then what?
No.
This would, let's just answer that. If this was 4, then this would be 2 sine 2 theta cosine 2 theta. Then you do it again. Then you do each of those down. One more. That's not going to happen. But all right, so here we get, hey, we got our 1/2 back. Didn't we? All right, so where are we at? Let's get an answer up here. We have 1/2 theta. Theta was secant inverse of t. And then we have 1/2 again, plus, now, all this information. Sine theta, going off my triangle, that's just root t squared minus 1 over t times cosine theta, which is 1 over t, plus a constant. And I'll clean it up a little bit. Not much, but a little bit. So, I just don't like the 2 t's down here like that. I'm just going to put them together. So 1/2 arcsecant t plus root t squared minus 1 over 2t squared plus c. Box it, that's your answer. All right, 1207. I think we need to do something harder. 45, perfect. It's like it knew I was asking.
I
Yes.
was going to ask you, I think was on the trig integrals, there was a question that was like 5 sine of 2x and cosine of 5x. And I didn't know what it was.
Oh, okay. Yeah. Let me address that. It was. Do you have it with you or no? Yeah. This is one of those ones that's in the internet class that didn't find its way into the face-to-face class.
Yeah, it's sine 2x, cosine 5x. And it's just a constant, so I don't think that it really matters.
That? Okay, so in your trig formulas, you have your formula sheets there, trig formulas? Let me see that. In the, where is it? I don't see it here. Well, that's not going to help. There's some formulas from pre-cal that are not on here because they're not used very often. It's the sum to product, product to sum formulas. So you might want to jot that down. And let me reference the page in the book. That way you'll know where to look for this. We haven't dealt with this before because we have different things inside, right? Like different arguments, 2x and 5x. So
It said
sum to product, product to sum formulas. Man, I don't know where it's going to be in here. I don't have them memorized. I just know that that's what we need. So let me see here. It might be Google time. Oh, nope, here they are. Okay, so it's an appendix. It's on A6, and it says this. Sine x cosine y equals 1/2 bracket sine x plus y plus sine x minus y, close brackets. This is what we would call a product to sum formula from pre-cal. And the great thing about it is that if you have two trig functions, sine and cosine being multiplied, then you can split it up and it turns out to be two sine functions with addition, which means you can integrate these individually, which will be easy because it's just sine. So for us, what's x in this formula for us here? 2x, and y is actually 5x. So this integral, the new integral becomes what? 1/2, which I'll just pull out. And then sine of x plus y. So add these two together, 2x plus 5x. So sine 7x plus, and then that one is x minus y. So that would be for us what? Sine of negative 3x dx. Does that make sense? And then at this point we integrate each of these. And so the antiderivative of sine is negative cosine, but then you have to scale by the a, then you have to hit it with the 1/2. So negative 1/14 cosine 7x. I'm going to erase this. This all right, or y'all following this? So this is 1/2 times negative 1/7 cosine 7x. So antiderivative of that is negative cosine, but then scale by the 7. This one over here is, again, negative cosine, but you scale by what this time? Negative 1/3. So you're going to have positive 1/2 times 1/3 cosine 3x plus c. So negative 1/14 cosine 7x.
And cosine 3x, you take out the negative?
The antiderivative of sine is negative cosine, but then we scale by negative 1/3. Negative and negative became plus.
Isn't there supposed
I
to be
mean, the
a
argument inside of cosine.
Oh, I forgot that. Well, I got lucky, actually. It wouldn't have mattered because cosine's an even function. So cosine of x is equal to cosine of negative x. But I did not intentionally do that. It's supposed to be negative. But it would have been, still would have been correct. All right. Thanks for bringing that up. All right, let's look at,
Real quick.
yeah,
Why is the 1/7 negative?
because the antiderivative of sine is negative cosine,
Oh, okay.
right?
Gotcha.
This next one is really the first problem that we've looked at, and we didn't look at this in class either. It's what we're going to start with today. Is a problem where things just aren't so obvious. So integral dx on top,
Is 45?
45, yes, thank you. A squared plus x squared to the 3/2 dx. That's it, that's the problem. So we assume here that a is a constant, that we don't know what it is, all right? Normally they just gave us a number like 4 or 9 or 1 or something. They've been real nice and they've given us a number, not this time.
Isn't there a way to split that up?
Well, I don't know what you mean by that, but you can't do this to that power, that to that power. You can't do that.
And she put it
Isn't
under
that
the
just
radical?
mean to cube root?
What does that mean? What? I'm hearing two different things.
Kind of like what he said, can she put it under radical, so the cube root?
Is that cube root though? So if you have this, this is x to the n over m. So when you do rational exponents, if you have a fraction up here as a power, the numerator is the power, the denominator is the root.
So it's square root of,
That's right. So this is really the square root of a squared plus x squared but then cubed, right? Cubed. You can actually put the cubed on the outside. So what I should say is that this right here is true, but this is also the same as the nth root of x then to the n. So this n power can come, you can do the nth power first, then take the cube root, or you can, or cube root, sorry. You can do the nth power of x first, then take the mth root, or you can do the nth root of x first and then take the nth power. The order of that does not matter. I'll give you an example. If you have cube root of 8 squared, right? What's 8 squared?
8 to the 2/3.
Yes, but I'm saying, we know that this is 8 to the 2/3, yes, but you could go cube root of 64, right? What's the cube root of 64? So what times itself 3 times gives you 64? 4 times 4 times 4? 4 times 4 times 4? So the answer here is 4, is that right? All agree? But I could also have done it this way, cube root of 8 and then squared the answer. So instead of squaring it and getting 64 first, I could have taken the cube root of 8 first, which would have been, it's a cube root of 8. 2, and then square it. 2, and then square it, and you get the same answer. So that's what I'm saying here, is that when you had this, I could have put the cubed in here like this, or I could have just cubed the whole root when I'm done. I'm choosing to do it this way. Why is it, do you think I would do that?
If you threw it in there,
It would be a lot more complicated.
Work with what's in there and then do with the cube.
That's right. What is this? What technique are we going to use for this here? The trig substitution. So we already know that when we do trig substitution, we wind up finding those 3 things, right? Whatever the substitution is, the derivative of it, and then the square root part. The square root part has always turned out to be something very nice, right? All we're going to have is that very nice thing cubed. That's all that's going to happen. So let's do this substitution. What do you do if you have your number squared and then your variable squared? What's the substitution we make?
Isn't that one also interchangeable?
What?
Like it's x squared plus a squared?
The second one here? Yeah, it doesn't matter which way it is. X squared plus a squared or a squared plus x squared, you use the same substitution.
The
A tangent theta. And in this case, a is what? A is a. We don't know what it is. So a is tangent theta. And then derivative of that is a secant squared theta d theta. And then the square root part of this. A squared plus x squared is a squared plus a squared tan theta, tan squared theta. Right. So you're squaring x. What can you factor out of both of those? A squared. You're left with 1 plus tangent squared theta. And 1 plus tangent squared theta is really secant squared theta. And that's just a secant theta. So you see now the difference, like when someone gives you what it turns out to be versus understanding where it comes from a little bit? I think it's a little better to know? Okay. It's more practice with algebra too, so it's...
Kind of made one of the first examples because it doesn't show you any constants, it just gives you...
Yeah. Yeah, so really you could say that anytime you make this substitution, right, this will always be your result, regardless of A. Right. All right, so you ready to rewrite this? Kiki, are we good?
You said 1 squared was not.
It was, this is this.
Okay, yeah, sorry, I was looking at wrong things.
All right, I would like to rewrite this integral, and I'm going to I'm going to rewrite it from this version right here. Integral 1 over a secant theta, right? That's this. A secant theta is this. But then what? Cubed. Dx. Dx is a secant squared theta d theta. Oh, that's nice. We got lucky. We got real lucky there. You see why?
Because it basically becomes cosine.
Yep, that's going to become cosine. So let's see.
Did we take the A out of there since it's constant? Or do we-
Yeah, we're going to take the a out, and we're going to have to make sure we get the right number of a's here. Let's see. We have equals. I'm going to write one more line. I'm going to cube the bottom. You have to cube the a and the secant. Ah. All right. So we get the secant squared to cancel out completely here with two of the factors. That leaves you with just one secant on the bottom. And then you have this a cancels here, and you get a squared when you're done. So we'll pull 1 over a squared out. 1 over a squared integral of 1 over secant theta d theta. 1 over secant is cosine, right? So 1 over a squared integral cosine theta d theta. Zach, are you good? All right. And that one, antiderivative cosine, it's about as clean as it ever gets, right? You don't even have to worry about the sign, the positive, negative, or anything like that. And that's it, right? Triangle. A triangle comes off the substitution that I made. That was x equals a tan theta, which means x over a is equal to tangent theta. X over a is tan theta, which means that this side is x squared plus a squared, square root. And we need what? Sine. So sine is opposite over hypotenuse. There we go.
Since there's a square root on the bottom, do we, like in pre-cal, we were told to push that up? Do we have to do that, or can we just let that be?
Push what up?
Like
Oh
basically-
yeah, no. You just leave it.
Cool.
What was the question?
Rationalize the denominator. Make that where the root's not down here. So you'd multiply top and bottom by this root. You don't need to do that. Let me check on what's going on at my house here. We're having carpet installed, and I had to leave the guys there.
I think your mic's still on.
That's all right.
We're just like, I'll edit that out later.
He looks confused. How's it going, man?
How you doing, sir?
Pretty good. Yourself?
What's that?
Yourself?
Pretty good.
Pretty good. What are you up to this semester?
Calcium.
Are you doing this online too?
Yeah, no, not online.
Face to face?
Yes, with
With who?
not sure his name is Alex, maybe?
Okay. Yeah. How's it going?
One okay.
Yeah. All right. Do we continue or what? Where are y'all at in your class?
The same thing. Too, sir.
Same thing? Okay. $47. Y'all want to try 47 yourself first? I'll put it up here.
Yeah.
And then I'll take a quick little break. I got to run to my office and get a couple of things for class. Got to print out that real big, there's a 5-question quiz that I'm going to be giving. I'm kidding. I'm kidding. No quiz. We don't have time for a quiz today. X squared plus 16 dx. So see what you can do with that. And if anyone 4 tan theta. 4 secant squared theta d theta. Square root of x squared plus 16 should be equal to 4 what? Secant theta? Right? Okay, and then rewriting the integral 1 over 4 secant theta dx is 4 secant squared theta d theta. Ah, this one's real clean. 4's cancel. You just get integral secant theta d theta. We good so far? And then that's just a formula, right? What is it? Natural log secant theta
Secant theta
plus tangent theta.
And then do the
Let's see.
triangle.
And then triangle. Triangle at this point. Oh, do they have something in here? Hold on. Let's see if they have a plan.
No, you were here first. Just kidding.
Oh, y'all want to come in?
No.
Oh, okay.
Sorry.
Get the hell out of
Yeah, problem.
here. X over 4. X over 4. Right? 16. Yes? And then you can get all your information here. So natural log secant theta was root x squared plus 16 over 4 plus tangent theta, which was x over 4 plus c. Right? And then you can get a common denominator there. I mean, there is a common denominator, I should say. Right? So when you put those two together, you get natural log square root x squared plus 16 plus x all over 4 plus c. And bet you that's not the answer in the back of the book. It may not be. I bet you they have this. They might have that.
What about the force?
Exactly.
Why?
Well, you see how these went together, right? Right? And that's this. Okay, remember the natural log. If you have natural log and you have division inside of a natural log, you can turn it into what? Minus. Right? So this turns into natural log of the top minus what? Natural log of 4, but natural log of 4 is just a number. A number plus a constant is still a constant. So you don't even care what that is because you don't know what that is. I'm betting that's what they have in the back of the book. So just FYI. I want something more interesting, like number 53. Can we do 53? This will be the last one I think I have time for. So I'm skipping 51, 49, and 51. So I'm going to make a mark here. I need to come back 49, 51. I need 23, 25. Okay, so I need to do those. So 53. X squared over square root 9 minus 25 x squared dx. Is that right? Is that what's there? Yeah? All right, so the point of me doing this one is to illustrate something that's pretty critical here. And that's in the formats that we have, right? This looks a lot like this format, right? Except that, you know, the implication here is that that's a 1 in front of the x squared. We have a 25. So you can't deal with that the same way. Understand? So what we need to do, there's a couple of options on how to do this. Different instructors do it different ways. I'm just going to show you the way I do it, okay? And you might see something different, a little different. Some instructors will just make this right here a 5x quantity squared and then do a basic substitution first. and rewrite the whole integral in terms of u. And then go do a trig substitution. All right, because this would turn into a u squared, right? But I do something a little different. What I do is I just force this to be a 1. So I factor 25 out. So I go like this. I'm going to factor 25 out, which means that this can't be a 9 anymore. It has to be 9 over 25. And then minus x squared dx. Do you agree that's the same thing? And then this root 25, since that's multiplication, can actually come out, right, as a square root 25, which is 5. Yes? Right, since that's times. I could break that into 2 roots, root 25 times root 9 over 25 minus x squared, right? That's the same exact thing. Then that root 25 on the outside is a 5. Had I factored out a 20, then I would pull out a root 20, because it's not a perfect square, but it's a constant, so it would just come out. So now what my integral looks like is this. 1/5 integral x squared over square root of 9/25 minus x squared dx. Do y'all follow that? No questions? You sure? Okay, so now at this point I can use the formula. It's a little tricky on what a is though. So the formula we're using, we're going to make a substitution. X is a sine theta. X is a sine theta. X is, what's a? 3/5 sine theta. So it's just the square root of that number. Square root top and bottom separately. Okay, Zach?
I was going to ask where you got the 5 from, but I realized it's because the 5 was on the bottom. So it's
5 was on the bottom, and then the square root of 25 gave us the 5. So dx is 3/5 cosine theta d theta. And our square root part that we have to rewrite, square root of 9 over 25 minus x squared will be equal to, this is where things get a little bit weird, 9 over 25 minus our x squared is 9/25 sine squared theta, right? That's what happens when we square this. I'm going to erase this, but y'all are going to have to remind me what it was, because that's the integral I'm going to be working off of, right?
9 over 25 minus x squared.
So, let's see, 9 over 25, then 1 minus sine squared theta, which turns into cosine squared theta, right? And then, I guess I'll just keep it here. So what is this? At the end of the day, after the root and everything. 3/5 cosine theta. Just remember that square root thing is going to turn into this. Do you have any questions on that? All right. So now I'm rewriting this equals 1/5 integral, x squared on top. So x squared for us is this squared, which is, what's that? No, okay, sorry, I didn't hear. 9/25 sine squared theta on top over the root part, which turns into what? 3/5 cosine theta. But then the dx part, which turns into, hey, is that right? Yeah. 3/5 cosine theta d theta. Right, this right here. That seems too nice. got 9/125ths integral sine squared theta d theta.
You could always try half angle.
Half angle?
Yeah, no, I don't want to do that. I was just kidding. It's gonna get ugly.
No, that's right, but why do you call it half angle?
Just to spite you.
I think that's what you did on purpose.
And why is that? Oh,
What?
no, I see. 5 times 25 is 1.
Power reducing is what I've been calling it, but yes, that's the right way. Right, so I'm going to rewrite here 9/250ths, because the 1/2 is going to come out of that formula, integral 1 minus cosine 2 theta d theta. So that 1/2 brought it out. Are we good? Are we good? Yay, nay? Okay, so now antiderivative of each of those, right? So 9/250ths, antiderivative of 1 is going to be theta here. So Zach, you're going to have an inverse trig function here at the end. And then the antiderivative of this is going to be, what, 1/2 sine 2 theta, but then there's a negative, so negative 1/2 sine 2 theta, but then there's a 9/250. So how about 9/500? Minus 9/500 sine 2 theta plus a constant.
Going after a 9/250ths.
Well,
Theta plus, or no?
you could. What I'm going to do, because of the next step, what I'm going to do is I'm going to leave it, because remember this sine 2 theta is going to turn into 2 sine theta, 2 cosine theta? This right here, right? The 2 that comes out is going to reduce this back to 9/250. Right? This is 2 sine theta cosine theta. So that 2, which is on top here, reduces out and becomes back to 9/250. Yes? Zach? No?
Absolutely.
We have 9/500
Times 1/2.
times, not 1/2, no. I'm saying this sine 2 theta is 2 sine theta cosine theta. The 2 is on top, right? And then 2 goes into 2 once, 2 goes into this 250 times. So it's 9/250. I just wrote it down here to show you what this is, but the 2 is on top. So because of that, my next one is minus 9/250 sine theta cosine theta plus c. I'm going to need a reference triangle. My original substitution was x was equal to, was it 3/5 sine theta? Was that it? Ooh, yeah, huh? What's what? What? Yeah, is that it?
3/5 sine theta.
Yeah. So we're going to make a reference triangle out of this, which is going to be a little weird. Because I'm supposed to divide both sides, right, by this number,
3/5 would be 5/5.
which is,
5x over 2.
yeah, so multiply both sides by the reciprocal, and it becomes 5x over 3, right? That's the way you should probably do it. 5x over 3. 5x over 3 equals sine theta. So that means this is 5x, this is 3, which means this is the square root of what?
25x squared.
And then this one 9, so 9 minus 25x squared. Hey, wasn't that the original root thing? It was, wasn't it? Before I factored out the 25. All right, I think we're ready. This is 9/250 theta. What's theta going to be? Come back to this right here. Arc sine of 5x over 3. Minus 950, or 9 over 250 times sine theta, which is 5x over 3, times cosine theta, which is root 9 minus 25x squared over 3, plus a constant. I think I'm going off my video here. And we have 9 minutes till class. We're almost there though. 9, that's 9 gone. How many times does 5 go into 25 to 250? 50 times? Can someone look in the back of the book? What number was this again?
53.
53. I've got 9 over 250 arc sine of 5x over 3 minus 1/50th x root 9 minus 25x squared plus c. Just going to see if that looks anything like the back. I'm sorry again, what number was it? 53? 6.2. Oh, it was a definite integral. I don't have the answer. You'd have to plug in numbers, but I think it's good. We could always take the derivative, but we're out of time. Huh? All right. More of this to come.